Hello, everyone. My name is Harshil Yerrabelli, and I'm a senior at Conard High School in West Hartford, Connecticut. And today I'm excited to present my independent quantum computing research project. And so my work focuses on hybrid quantum classical circuit design, specifically how we can integrate classical reversible logic into quantum circuits to optimize computational efficiency. So in this presentation, I'll take you through the motivation behind the research, objectives, experimental and simulation methods that I employed, key results, and finally some conclusions regarding scalability, energy efficiency, and error reduction. So first, background and motivation. So my project is based on really the promise of quantum computing, which is one of the most promising tech advancements right now. So, first, how does it actually work? So, unlike classical computers, which can process bits as either 0 or 1, quantum computers use qubits that can exist in superposition, meaning they can be 0 and 1 at the same time. And additionally, there are these properties. For example, quantum entanglement, which allows qubits to be interconnected such that the state of one instantly influences the state of another. And these properties offer the potential for exponential speedups in solving specific problems. So in the slide, you'll see a diagram that highlights these key quantum phenomena. So, however, while the theoretical potential is enormous, practical implementation faces many hurdles, which brings me to the next slide. So, despite the promise of quantum computing that I talked about earlier, current quantum hardware is far from ideal. So, one of the biggest challenges is noise. So, errors due to decoherence and operational imperfections. So, qubits are highly susceptible to environmental disturbances. So, and because of that, they have to be in a very cold environment. And because of this, this results in high error rates. And additionally, in our current state today, quantum processors have a very limited number of qubits, meaning they can only maintain quantum states for a brief period before error set in. And so this slide visually represents these challenges with error bars and noise symbols. So now the other side of computing, which is the computing that we know and use every day, which is classical computing. So this type of circuits with classical is very reliable with deterministic operations in near zero error rates. And they excel in simple arithmetic and logic operations. However, classical computing struggles with certain types of complex problems, especially those that grow exponentially in complexity. And so this slide illustrates how classical bits and deterministic logic can solve many tasks efficiently, but as problem sizes increase, the computational resources required can become prohibitive. So now this brings me to the hybrid approach that I propose. So this is designed to combine the strengths of both quantum and classical computing. So specifically in this research, um, I tried embedding classical reversible logic, such as Toffoli or Fredkin gates, into quantum circuits, where we can reduce the number of purely quantum operations needed. And so this integration minimizes quantum gate overhead, lowers circuit depth, and thereby reduces the probability of errors due to decoherence. And so, in other words, we can leverage the energy efficiency and reliability of classical logic while still taking advantage of those properties described and offered by quantum mechanics. And so in this diagram here shows a typical quantum circuit where some operations are replaced with classical reversible gates. So, in summary, quantum computing's exponential potential is currently limited by hardware imperfections and noise. In classical computing, while efficient and reliable for many tasks, simply cannot scale to solve complex problems. So, this hybrid approach seeks to bridge this gap by combining the deterministic low energy nature of classical circuits with the power of quantum parallelism. So now moving on to the research itself, so the experimental setup and methodology. So first was the hardware setup for classical circuits. So in order to compare with the quantum approaches, I first built classical circuits on a solderless breadboard. For example, I constructed full adders using standard electronic components, such as transistors, resistors, LEDs, and CMOS logic gates. And so next comes uh, the component interactions. And with these interactions, we can like measure the factors like execution time and energy consumption in these classical setups, where I try to establish a performance baseline with this hardware setup. So now moving to the heart of the project, majority of the project, which was through the software tools in simulation environment. So on the simulation side, I used Qiskit for designing and simulating quantum circuits, taking advantage of IBM's AER simulator. And in addition, I utilized PennyLane for constructing and simulating hybrid circuits. And finally, I tried using advanced techniques, such as noise-aware transpilation, like ATOM, which is a machine learning optimizer, which were employed to further refine the circuit designs. So this slide is the pure quantum circuit design. And so in these circuits, every operation is performed using quantum gates. For instance, you might have a circuit designed for quantum full adder or a QAOA circuit solving a max cut problem. While this design takes full advantage of the quantum properties, it also suffers from high circuit debt and increased error rates due to the sheer number of quantum operations. So here is a hybrid circuit designed. So in this approach, classical reversible logic gates, such as the Toffoli, which is notated as CCX, and the Fredkin, which is notated as the C-swap gates, are integrated into the quantum circuit. And these gates perform those deterministic reversible operations that help to reduce the total number of quantum gates required. And so finally, the third step of the software approach, which is the circuit optimization techniques. So one major approach under this was the noise-aware transpilation, and this process reorders and optimizes the sequence of quantum gates to minimize circuit debt. And additionally, I tried employing machine learning optimizers such as the Atom optimizer with multiple random restarts. So now to the actual results. So here is first metric, which was execution time, so speed. So while classical circuits are almost instantaneous for simple tasks, pure quantum circuits require significantly more time due to the complexity of maintaining quantum coherence. And this hybrid approach, by integrating classical logic, managed to reduce the execution time to around 0.002 seconds. Although it's slightly slower than the classical circuits, the hybrid method strikes a balance between speed and reliability. The next metric is accuracy and precision. So for simple operations, classical circuits are near perfect, but when the complexity increases, accuracy can drop. So first I examined the pure quantum circuit, and that achieved an accuracy of 75.3% with an output variance of 8.9. With the hybrid approach, The accuracy was 92.7% with the variance of 4.1%. And so
2 minute warning.
thank you. The improvements indicate that the hybrid method not only reduces the error propagation, but could also provide more reliable and precise outcomes under the noisy conditions. So thirdly is energy efficiency. So here pure quantum circuits typically consume 6.1 MW and involve a high gate count of 41 gates. And the hybrid circuits reduce the number of gates to roughly 34 and consume only about 3.2 MW per operation. And finally is the scalability analysis. So while both pure quantum and hybrid circuits see an increase in execution time as the number of qubits or operation grows, the hybrid design scales better. And this scalability advantage is crucial when we consider the large-scale computations in which these approaches would be used. So now to the discussion. So the findings was that the hybrid approach is its ability to significantly reduce the quantum gate overhead. And so pure quantum methods have potential but are limited by noise and complexity. And classical methods are optimal for the trivial tasks but do not scale. And we tried, and so in this research, we tried to implement the advanced noise models and run tests on the real hardware with by trying to use the reinforcement learning for optimized gate reordering. And finally, one next step that could be used is exploring further applications in cryptography, AI, etc. So with that, I'd like to conclude my presentation, and I'm open to any more questions.